All right. So let's continue. If there's any issue with the technical, visual or audio, please let me know. All right. So we were discussing. Sure again. Okay. So we were discussing the topic, right, of the list of common continuous random variables. And the first one, right, we went through is the uniform, right? Where the uniform basically, right, true to the name. Sorry, let me. Get the new one here. Right, the uniform, true to the name, right, has constant, right, density, right, over the support, right, of the uniform, and the expectation, right, is right in between, right. So right in between, right, is where the expectation is, and the variance, right, represents the spread. How far is it, right? Divided by 12. Again, this 12 doesn't have like a meaning, right? It's just basically a relic, right, of how the calculation goes, okay? And it will be used to, right, model the arrival time of an event that basically you have no information about how that time happens. It just happens uniformly, right, between two time interval. Well, what's the difference? The difference is in contrast with something like an exponential, where you see that, right, you have a much higher density starting out and it goes exponentially down. So something like this, right, is not uniform clearly, meaning that the likelihood of the event happen at the beginning is much higher, right, than the event happens toward the end, if you want to use that as a time model, right? But for a uniform, okay, like a bus, right, or whatever, right, it's up to you. But basically what you're saying is that you have no knowledge, right, of how the bus arrives throughout this interval. It arrives randomly, but it could arrive at any moment, right? There's no preference. Like the bus is not like more likely to arrive toward the beginning or toward the end of the interval. Okay. So that would be the continuous, right? Random variable. Sorry, uniform random variable, right? One thing to remember about the uniform as well is that it basically is the continuous analog, right, of the equilikely sample space that we talked about. So in other words, right, so remember that when you compute probability, right, of a random variable, what you usually have to do is to integrate, right, from C to D, the density dx. You can integrate the uniform, right? But the answer would be this, which is kind of pretty clear, right, coming from here. So, but a more intuitive way to memorize this or to remember this is that basically, right, is the proportion. Right, is proportion of CD over the proportion of AB. All right. So basically, the probability is just proportional. So in that sense, right, how much you are in CD over the total numbers is a probability. So that's like a continuous version of the equal likely outcome, right, for the discrete case. Okay. Any question about this? So let us take a look at which is this one, right? So let's take a look. All right. So notice here, right? In contrast to the advertisement about arrival time of train or bus, right, as uniform, here in this problem, right, trains arrive at the exact moment, right? So at a fixed moment, which again is kind of not the way train arrives, but that's a problem, right? But the passenger is the one who arrives randomly, right? And then your task is to read the description, right? And of course, the behavior is a bit weird too. They get on the first train that arrives, right? What proportion of time do they go to destination A? What will be the answer here? How would we figure out the probability, right? That the person goes to destination A. So if we look at this, right, this represents the interval from 7 to 8. And the person, right, would have to arrive in these intervals, right? Here to go to A, correct? So in terms of the uniform distribution, basically it's the proportion of time the person arrives around these intervals divided by the total length of time, which is 60. Right. Okay. And how long is that? How long is this time interval? Well, that's 10 seconds.
Oh, well, there's 4 of 10 minutes, so it would be 40 minutes over 60 minutes.
Correct, right? So the answer in part A would be 40 over 60, which is 2/3. Right? Right. What about part B? How will we answer part B? Well, it's the same kind of question, right? But now we have to switch the window from 710 to 810, right? Which I guess goes above this picture a little bit. But if it's 710, then the first interval A actually is only from here to here, right? And then is anything beyond this that we should look at? What happens after this? So B, right? The next time will be 805, right? For B, right? But then 810, right? Which is the last one, guaranteed to be 8, right? So I mean by B here, I mean the B bus arrive here, right? So this interval will also be A. Correct. So the probability for that will be still, right? 40 over 60, right? But notice that it's 40 over 60 with a different split of the intervals, right? These three stays the same, but this is a 5-minute interval and this is a 5-minute interval, right? Told you that. Any question with this? Right. Okay. So notice that we'll just write down the answers, but in your answers, you have to kind of list out the intervals or something like that, right? That's a justification for your answers. Okay. All right. Okay, let's take a look at question 8. Okay. So for this, there is a small question of interpreting this statement, right? Meaning the statement of a point being chosen randomly on a line segment of length L. So symbolically or probabilistically, right? What do we mean by this? What does it mean to choose something randomly over an interval?
That would be,
Well,
uh,
go ahead.
yeah, it would be the uniform PDF that we were talking about before, I think.
Right. So if you let the x be the location of the point, right? Then what we're saying is x is uniform from 0 to L, right? So x is as a random variable, right? Is a uniform random variable. All right. But that's kind of just a small part, right? The big part is about the probability that the ratio of the shorter to longer segment is less than 1/4. So if you let R be the ratio, right? Short over long, then this is probably r less than or equal to 1/4. The challenge here, of course, is to relate r to x. Right? How would that work?
This might be wrong just because I kind of like implicitly thought about this in just one section, but I kind of just thought about splitting the length into 5 pieces of equal size. So then if it was to just land, I just focused on like one of the pieces, if it was to randomly choose just one piece, then that probability would be 1 to 5, like 1/5, because that's the case that the shorter to longer segment would be 1/4, right?
Uh, yeah, but that's wrong in the sense of you try to hit the exactly equal, right?
No, like
And go ahead.
does that take into, well, no, I was thinking about that. It's not possible to hit exactly like 1/4.
Mm-hmm.
So, okay, I don't know. I thought it would be one.
No, that and also I think that's a bit that's actually a bit really on the nose of the interpretation, right? We should relax that a little bit. So in the sense of, right, here's 0, here's L, right? And X is somewhere right here. Okay. First of all, on this picture, where is the longer segment?
Well, the right half, like the right side.
Yeah, this is a longer segment, right? And this is obviously just shorter segment, right? So what is R in this case? How is R represented in terms of X?
X over L minus X.
Yes, correct. But is that always true?
For
Is
any,
there a case where, go ahead,
well, for any
but
X, oh no, it's not always true. If it's past like that 0.5 uh mark, then it wouldn't be true.
right? So where is it true though? Is this
Uh,
true?
for X less than 0.5 or in between 0 and 0.5.
Uh, Not 0.5, but L over 2.
Oh, right. Okay.
No, it's fine. Right, we have L here instead of 1. But all right, but what if it's over here then? Then what happens? Where's the longer and where's the shorter segment? This is longer, right? This is shorter. So R is going to be
The reciprocal of that, L minus X
exactly
over X. Yeah.
right. So L over 2 less than X less than L, correct? And so, right, actually there we have it. Because what does it mean? For this probability to work, that probability will be probability of X over L minus X less than 1/4, and X is between 0 and L over 2, plus probability L minus X over X is less than or equal to 1/4, and L over 2 less than X less than, right? How do we deal with this? And then, right, we will know how to deal with that similarly. How do we deal with this? a natural thing to do is to multiply, right? Correct? And then the other one, same thing. Correct? And then this becomes what? 5x less than or equal to L, or that is right. And then this is 4, right? L 5. So correct. How do we finish these calculations? Well, clearly, right? Is 2 just subsume 2? And then the other one subsumes 2, right? And now by proportion, this is L over 5 over L, or 5th L over L. Sorry, not 4/5. 1/5 also, right? Because the length, right, from here to this, I guess, right, what happens is it's less than or equal to L, right? So that's also, if you want, this is L minus 4/5 L, right? What the final answer is? 2/5. All right, any question about this? All right. Okay, so let's take a look at this. All right. So first of all, do we understand what this question is aiming to ask, or how do we translate this question to a mathematical question? The first thing, right, is that right, there is a 100 miles interval, correct? where a uniform random variable, right, which is the bus's breakdown location can happen, right? It can happen anywhere uniformly, right, on this road. So the service station, right, or there are two competing claim, right? There's A, there's B, right, and there's C, right? These are fixed location, right, which service the bus, right, if there's a breakdown. So this is, let's call this plan one, right? Plan number two, instead, we'll put it where? 25, 15, 75. So I guess it'll be A prime, right? C is actually the same, right? But just call it C prime now. A prime, B prime, right? Plan number two, right? So the question is, which one is more efficient? Of course, we haven't written down any quantities here yet, right? We just draw a picture. So now we have to interpret the word efficient, right? So what random variable or what quantity of interest? What random variable are we looking at? Because you have to identify it, right, to be able to answer this question. So what are we looking at? We do have, right, a random variable, which is x, right, which is uniform from 0 to 100, right, which is the location of breakdown, right? But what quantity are we interested in to talk about efficiency?
Probably the distance from the breakdown to the nearest station.
That's correct, right? Exactly. That's very good in terms of English description. That's very good. We want to look at the distance, right, from X, right, to nearest service location, right? Exactly. But now let us well, you know what? Let's work with this. Let's look at, right, this quantity. First of all, right, let's just put a handle on this. What kind of quantity is this? Is it a number? Is it a numerical value, or is it a random variable? Is it a fixed number? That's what I'm trying to say. Is it a fixed constant, or is it a random variable?
No, it's a random variable.
Good, right? Of course, it's random. Right? It's a random variable. So let's call it D, right? So let's call D1, which is under plan one. Can anyone describe to me what D1 looks like? What this distance to the nearest location looks like under plan one? Of course, description here means description in terms of X. What does it look like?
So I'd say from the first thing, x being between 0 and 25,
Good,
it would just be x.
excellent.
Okay. And then from 25 to 50, it would be c minus x, or wait, c, right? Yeah, c minus x.
No, I mean, there's no C here, right? 50, right?
Oh, wait, right.
I mean, C is just a name, right? Yeah, 50. Good.
Yeah, that's why I tripped up for a second. I wasn't sure if c was the placeholder for the value. I forgot we were working with like an actual number, 100 being the, okay.
And then
And then,
50 to 75,
yeah, that would be x minus c,
X minus 50, right?
or
Mhm.
yeah.
Good.
And then the last one would just be 100 minus x.
Good. So that's the distance, right? Under Plan one.
Yeah.
Very good. What about plan two? What about D2? What would that look like?
This one's a little more complicated, but the first one would be, I think, just between 0 and 25, it would just be x.
No,
Wait, what are the numbers again? Is it 25, 50, and 75 that it splits up?
that's true, but it's not X, right? Because where's the service location? A prime, right?
Oh, okay, okay. Yeah. So
So
25, yeah, 25 minus x.
correct. Okay. And then
And then, well, the midpoint of 25 and 50. So what is that like?
what is it? 37.5.
Yeah.
Okay, that would be.
That would be 37.5 minus x.
Hold on. No, right? It'll be X minus 25, isn't it?
Oh, right. Yeah.
Right. And then beyond that,
So, so that would be 50 minus x.
correct. And then 52, 62.5. That would be.
X minus 50.
Mm-hmm. And then I guess 62.5 to 75, right?
Yeah. So 75 minus x for that.
Uh-huh. And then we're not done yet, right? Beyond 75, X minus 75. Right?
Yeah.
All right, good. So these are the random variables, right? That these are two random variables that describe the distance from X to the nearest service location. So we have described it, right, completely. Right. But the question is, which one is more efficient? So how can we decide based on these two random variables?
Yeah. I think you can just calculate the expectation of each and then compare them.
Very good. Exactly, right? So we would calculate expectation of D1, expectation of D2, right? Compare and pick the smaller one, right? Good. All right. Any questions so far? Okay. Now let's talk about the computational aspect of it because I suspect that many of you would already do something funny, right, with this kind of calculation by, as in, asking, right, AI help and things like that. Let's take a look at D1, for example. See how I can do it. So how would I calculate expectation of D1 here? Just describe it to me verbally. We don't have to like do the whole thing. How would I calculate expectation on D1? kind of integrals do I have to set up? I have to set up 4 integrals, right? From 0 to 25 of x over, remember it's the uniform over 100, right? Dx. Plus the integral from 25 to 50 of 50 minus x over 100 dx. Plus the integral from, 50 to 75, and then the integral 75 to 100, so on. All right? So that's all you have to do. Now, there is a saving device here that we can do to help us not calculate all 4 integrals, which is what?
Can we just ignore the last two and multiply by 2?
I think you can do better. I think all of them are equal by symmetry, actually.
Oh,
So you can do first one and multiply by 4. Okay, so let's demonstrate that at least. So for example, right, let's demonstrate the first 2 are equal, right? And then you can trust it, they're all the same. For example, it's x squared over 2, right? And then 1 over 100, right? 0 to 25. So it's really 25 squared, right? Over 200, whatever that is, right? This one, right, is minus 15 minus x squared, right? Over 200, plugging 25 to 50. You see, the answer is also 25 squared over 200. Is that okay? So, right, you just have to do one integral and multiply by 4. But you should recognize it's 4 integrals together. Any question about this? What about the second one though? D2. How many integrals do I have to set up? 1, 2, 3, 4, 5, 6, right? So what does that mean? We can just calculate 1 and multiply by 6.
I think we have to do 2 here.
Right. So this and this are the same, I think, right? And all these 4 are the same. So calculate this times 2 and calculate this times 4. Agree? And while we're at, right, I was saying expectation of D1 is 4 times 0 to 25 x over 100 dx. Any question? All right, so yeah,
No, I just wanted to ask if we can just integrate and like you don't have to plug in the, whatever it is, the 25 into X or something. We can just kind of leave it in that like evaluate form with the bar and the numbers of integration. You know what I
oh, you
mean?
do have to you do have to integrate out, actually. You have to get out the numerical values because eventually, you mean you just leave it like this? Is that what you're saying?
No, no, like I was gonna integrate it, just leaving it like one row above what you just circled. You know what I mean?
So this is acceptable. This is good. I guess here is still a little bit not yet, right? This one.
Oh, okay,
I
that's what.
mean, if you're asking, you have to know what 25 is, 25 squares. No, you don't have to. Or you have to know 12.5 squares, blah, blah, no. So the answer could be in the form of, for example, right? I don't know, 37.5 minus 25 squared over 200, whatever. That's perfectly acceptable. If that's what you're asking, but it has to get there, right? It has to get to that before. Well, of course, I'm not asking you to like square 17.5 or something. Is that okay?
Yeah. Thanks.
All right, sure. But you're right. I mean, like, so that's kind of like acceptable answers, but just say you have access to, right, calculator and stuff like that at home, or not, whatever. What do you think? Which one is smaller here? Just from pure guessing.
I think the expectation of D2 is probably smaller.
Yeah, it would turn out that D2, right, is the better plan here, right? Kind of intuitively seems to be okay here, right? You're always A here, right? You're always close to A. A is a better location. A prime is a better location than A, and B prime is a better location than B. But right, I mean, like again, we could talk about intuitive and things like intuition, things like that. But right, the real justification will have to go through the calculation. All right. Any question? And let me explain to you why the reason has to go through the calculation and justification. The intuition that plan 2 is better highly relies on the fact that the breakdown location is uniform, right? In reality, right, breakdown location probably is not uniform, meaning that maybe it's higher at some part of the road and lower at some other parts, right? I mean, if the breakdown is like that, this is the density of the breakdown, right, which is not uniform. Then what do you think? Which plan seems to be better now? Plan 1. Do you see that? Because the breakdown is more likely to happen at toward the two ends of the road rather than the middle. Are we okay? So I'm just giving you some scenarios to show you that, right? So notice that the formulation are the same, no matter what the PDF is. It only changes, right, at the point where you have to do this actual calculation. Here we do over 100 because, right, it's uniform. But if it's some other PDF, then you have to multiply with the PDF, right? You understand? And that will change, right, the calculation. Then you may not be able to use symmetry to avoid calculating all 4 pieces or 6 pieces out if there's no symmetry, right? So here, right, we can cut through a lot of calculations because again, the problem is simple and it's just meant to be simple, right? Simple-ish. But the problem can be much more complex with a different PDF. Right? And of course, the answer might not be the same. As in, like the choice of D2 is better. Right. Any question? All right. All right, so let's take a look at question number 10, right? Is that, yeah. All right. I mean, there's not much to this question, right? Besides interpreting the statement. The bus arrives from 10 to 30, right? You have to wait longer than 10 minutes is the same as the probability that the bus will arrive from 10:20, right? Sorry, 10:10, right? Arrive after 10:10, right? Which of course is 2/3, right? So that's easy. What will B though? What kind of question is B? So B has the word if, right? So that signals a conditional probability question, right? So I guess we can use the notation X here, right? X is the bus arrival time, right? So probability B is conditioned on X bigger than equal to 15, let's say, right? We can ignore 10, right? X will be uniform from 0 to 30, right? Because that's the time of arrival, right? So we know that X is bigger than equal to 15 because the bus has not arrived by 10:15, right? And you have to wait longer than 10 minutes after that. So that's X bigger than 25, right? Of course, you have to now use the definition of conditional probability, right? So the top is, of course, is X bigger than 25. So it's 25 over 30 divided by, right, 15 over 30, right, which is, of course, over, where am I? Sorry, not 25. I'm not thinking, right, 5, right? Because 25, right, to 30 is 5, right? So that's 5 over 15, which is 1/3. Right. Any question about this? So notice, right? So this question is very simple. All right. But there is a point to it. And the point is actually connected to what we'll be discussing next about the exponential random variable. Notice, right, both of them have the statement about wait longer than 10 minutes, right? Of course, right? The second one is conditioning on you, or you have waited 15 minutes. But you can still, right, view this as 15 plus 10, right? 25, 15 plus 10, of course. I mean, again, that's not the point. The point is, right, the answer here are different, 2/3 and 1/3, right? And again, you might not feel surprised, or why would you have to be surprised here? The thing is, this is actually the state of thing, actually, right? Nothing to be said. But what will be surprising, or what the characteristic of the exponential random variable is that for the exponential random variable, these two will be the same. Okay, these two will be the same, and that will be called the memoryless property for the exponential, meaning that it doesn't remember this part. It's only care about the plus 10 part. Of course, right? It also goes without saying that the uniform is not memoryless, right? So all this un, don't have to be set at this problem, right? At the level of this problem, you just have to do these calculations and be done with it. But I just want to explain to you why this problem is here, right? It serves as like a counterpart to what you'll be seeing about the exponential random variable. All right. Any question about this? Okay. So this is question 11. I think let's save this until after the quiz. Let me talk a little bit about the remaining part of the uniform, and then I'll give you the quiz, and then we'll talk about the other problem after the break. So one thing that may seem trivial to you right now is the aspect of scaling, right? And translating a random variable. So by scaling, of course, is when you multiply a random variable by a constant. And by translating, when you add, right, a constant to a random variable, right? And those of you who have taken some statistics / maybe probability, you should have seen this via the Z transformation, right, for the normal random variable. The question, of course, is, right, when you do this, does a random variable stay in the same family? Meaning if you scale and you translate, does it stay as a uniform? The answer, right, here doesn't surprise you or anyone, I guess, is that yes, right, it does. So you scale and translate uniform, you stay uniform. But do not take this for granted in the sense that it's not always true. In other words, this will fail, for example, for the exponential random variable. All right, that we'll be talking next. So the point is, there's just small things that you feel like obvious, whatever. But if you don't pay attention and you kind of generalize that obvious part to all cases, then you'll make a mistake, right? So I'm not trying to say that there's a big deal here, but kind of try to think about why it's true to begin with. And then you see when we talk about exponential why it's not true, right? Any question? Okay, so let me give you a quiz, right? So the question for the quiz will be question 7. Should not give you the answer, right? Um, all right, so this will be the quiz question. All right, any question before we take a break? All right, if not, then we'll resume at 7:05. let's continue. Is there any question before we continue? All right. So I guess let's take a look at the next question, which is this one, right? So I think, well, right, the problem basically spells out everything for you, right? So we have a uniform random variable, right, from 0 to L, and then 0 to A, I guess, big A. And then I guess to save the confusion, well, whatever, you can call it A too. And then, right, you want to choose little a, right, to minimize this. So the problem, of course, is to minimize, right, overall A between 0 to big A, right? Like that. So I guess let's first try to see what this is, right? So expectation of x minus little a is the integral, right, from 0 to big A of 1 over a x minus a dx, right? That's by definition of the expectation of uniform. All right. Now, then what can we do with this in order to answer this question? What should our next step be? Well, the main goal, right, is to calculate this out as a function of little a. Right, whatever that is, so that you can minimize that function over the closed interval, 0 to big A. Does that make sense? Okay. So as it stands, what can we do to calculate this integral? What we should do is to take care of the absolute value, right? Which will be 0 to little a minus x, and a to big A, x minus a. Is that okay? Any question about this? All right, so just go ahead and do the calculation, right? That will be a minus x square over 2 with a minus sign. So the answer here will be a square over 2, right? And this will be a minus a, big A minus a. Right, that's our function. Okay. All right. I guess calculus 1, calc 1 here, right? What do we need to do next? we will differentiate, right, with respect to little a, and then set equal to 0. Right? And the equation leads to that's the answer for the minimizer, right, of this expression. All right, any question about this? So let's take a step back, right, at this problem and take a look. What is this value? Is this anything special in terms of the uniform? Is a over 2, is big A over 2 a special value in terms of the uniform? 0 to A?
I think is a median, right?
It's excellent that you mentioned the word median. It's actually excellent, because actually the one that people would think of first is the expectation, right? Which is correct here too, right? But it's excellent that the concept median is brought up, because so, right, what is the median of x? Let's call it x hat, right? Then the median of x is a value, right? Let's call it x hat, right? Is a value such that the probability x less than that value is 1/2, right? It's the value that split the distribution 50% to the left, 50% to the right. Now, for symmetric distribution, right, something that looks like the normal, for example, or right, uniform, then the mean and the median, sorry, here, right? So I guess let's call it, I remember the notation I want is mu hat, right? So for symmetric distribution, the mean and median are the same. And so there can be a confusion. I mean, not confusion, but right, they're not distinguished for non-symmetric, for symmetric distribution. The reason it's brought up is because now the subtle point for this is, right, this is expectation of x minus a, which is called L1 norm optimization. This, in this day and age, might have some connection to, right, machine learning and AI and all that good stuff, because all they do is optimization. But if you ever look into any of those things, then the most popular norm that are used, by no means, right, you know, the best or whatever, it's just the most commonly used, is the L2 norm, which is expectation of x minus a square, right? And a point that might be underappreciated is that these two problems are not the same problems. Or I hope at least you kind of vaguely feel that it cannot be the same problem, because it look at two different functions, right? Two different value functions. So in that sense, the answer to these two questions should not be the same in general, right? And the abstract general answer, it can be proved, but a bit beyond our class, that the answer, the abstract answer in general for this is the optimizer is the mean for the L2 optimization. And the L2 and the L1 optimizer is actually the median. So it's excellent that your friend there mentioned the median concept, right? But here, right, it kind of all collapsed down to one single answer because the uniform, right, is symmetric. So you don't see the distinction between L2 and L1 optimization. You don't see, right, the mean versus the median. We'll have a very similar problem coming up in the next problem set that deals with the exponential, which is not symmetric. And there you will see the difference between the mean and the median. Okay. Any question about this? All right. Yes, that is the last part of the problem set. All right. So let us go back to the lecture. So the next random variable we want to look at, right, is the exponential. Okay. So the exponential has density lambda equals minus lambda x. We kind of talked about, right, last time when we want to use this property to deal with right, calculation in a quick way. But notice, right, its support is from 0 to infinity. Right, that cannot be changed. I mean, you can change it, but then the name of that random variable is no longer exponential, right? No longer the classical exponential. Okay. And also notice it has infinite support, right? 0 to infinity, versus, right, the uniform, where the uniform is finite support. Okay. And so this should be kept in mind for many reasons. Right. The first is, right, it's also used as a time model, right? Like the time it takes for an instrument to malfunction. Okay. And here we're going to talk about like kind of the aspect of modeling. Okay. I mean, because a lot of times, well, in this class, you don't have to deal with modeling, right? Because you just accept whatever the question is telling you, right? And you just work with the random variable. But beyond this class, or when you want to do work, you know, on your own, whatever, right? And you might have to choose a model, right, that fits whatever you're trying to look at, right? The phenomenon you're trying to look at. So you want to be aware, right, of the what you're committing to when you, let's say, use an exponential as a time, right, as a model for the time of the event. The first thing, of course, is the infinite, right, support, which may or may not hurt, right? We talk about this with the Poisson, right? Poisson is routinely used to model, right, things that have finite as an upper bound, like the number of typos on the number of typos, right, on a page, or the number of customers arriving at a store, right? The reason is, of course, right, you cannot pack like 1 million customers into a store, right? So physically there is a limit. But understandably, that's an approximation, so that's fine, right? And modeling has that aspect. So the infinite support should not hurt too much. What really is more of a commitment that people may not recognize is the memoryless property. Okay, we'll talk about that later. But also, right, notice that there is also the non-uniformness, which, right, of course, it's not uniform, so it's non-uniform. But you may not recognize that that's what you're committed to as well. Right, let's look at, for example, the time it takes for an instrument to malfunction. Well, if you do use an exponential, right, to model, then you are kind of saying that the likelihood, right, of the instrument breaks down at the beginning of the cycle is higher than the instrument breaking down at the end, right? Which, right, actually is not what we think, right? we think that the likelihood of something breaking down when we first buy it is small, and then it might rise up again. Maybe that's how I think. Maybe that's not how you think, right? Whatever. But if I think like that, meaning a new thing is less likely to break down, right, compared to an old thing, then maybe the exponential is not what I'm having in mind, right? So those things, right? Again, small beyond this class because you're not really doing modeling. But I just want to kind of, well, at least that this kind of discussion helps to bring these random variables to you alive, right? They're not just symbols, mathematical things that don't do anything, right? They do tell a story of their own. All right. And then of course, right, there's the lambda, which is about the rate, right? The rate. Well, what kind of rate though, right? The lambda here, right, also tells a story. Notice the lambda works in an inverse fashion, meaning the bigger the lambda, right, the smaller the expectation and the variance. All right. So it works in the opposite way, right, compared to the Poisson. And in fact, right, that's the whole point. The exponential and the Poisson actually comes as a pair. I mean, in some circle at least, in the stochastic process circle, right, the probability circle. I mean, in statistics, I'm not so sure if unless they do modeling, right? So the point is, right, a Poisson lambda is intimately connected to an exponential lambda in the sense that if you have the Poisson to model, right, the count of the events, like the customer arriving, right, in at a store in 1 hour, like Poisson 3. So what you're saying is that on average, right, there are 3 customers arriving, right, at a store in an hour. Notice, right, the expectation of the Poisson is exactly lambda, right? But when you look at the time, oh, sorry, I haven't said it, right? So when you do that, then the exponential exactly models the time between the events. So it's called inter-arrival time, right? In other words, something like this, right? 0 to tau 1, that's the first customer arrive. So the Poisson goes up by 1. And then there's a random time, tau 2. So, sorry, from tau 1, right, you add a tau 2. So at this moment, it's tau 1 plus tau 2. So the Poisson go up by 1 more. So 2 customers have arrived. Right, and then there's another moment here, let's say very short. Right, so this interval here is tau 2. This interval here is tau 3, right? So tau 1, tau 2, tau 3 are exponentials, right? They're inter-arrival time. But the reason why we have to stress that is you have to kind of distinguish it from the time of the event. Right? In other words, notice the first customer arrived at tau 1, the second customer arrived at tau 1 plus tau 2, the third customer arrived at tau 1 plus tau 2 plus tau 3, right? That's not exponential. That's a sum of exponential. So it's called, it's a gamma distribution, right? But anyway, so the inter-arrival time, right, are exponential. Or, right, if you think about it, if on average 3 customers arrive in an hour, then on average, the inter-arrival time, right, the time between events is 1/3. So the connection between lambda and 1 over lambda, right, is exactly on point. Do you understand? Now, you want to keep this in mind because, right, if you go on or beyond after this class, you take like at Rutgers, you take 481, right? It's called mathematical statistics or parametric statistics, right? Then you will also look at the exponential lambda, but there the exponential lambda will be defined as this, right? It's one of those things where, you know, blink and you miss it because, well, didn't you just say this before? The answer is no. What you saw was lambda e to minus lambda x in the density function. That's the definition. Okay, what's the big deal? No big deal. The calculation will just have to come out like that, right? For the exponential. And you'd be like, well, isn't this better? Looks like nicer. I don't have to invert it. Okay, that's exactly why the statistics people use it this way, right? Because they want to estimate lambda. So they want to have it come out this way. So they estimate with the sample mean, sample variance, that kind of thing. But for us, if you do it like this, then you cannot associate this guy with an exponential, with a Poisson lambda. In fact, right, if it's this way, then you have to associate with a Poisson 1/1 lambda. So for us, or for me, or people in my circle, stochastic process, whatever, right? We have the Poisson in mind, going hand in hand with exponential. That's why one of them, right, will be the rate, right, will be 1 over the average number of events. And of course, then the exponential, right, naturally has that. But, so, right, so I'm just telling you this, but the convention, right, or in this class, when we mention exponential lambda without any qualification, right, this is what we mean. We don't have to spell it out for you every time. All right, any question?
Professor, is this model also the radioactive decay one, like the half-life thing?
Yeah. I mean, again, you kind of throw in some extra words like radioactive, right? I mean, who knows? Decay can follow a lot of model, right? This is exponential decay, right? And of course, I do know that maybe the radioactive stuff decays exponentially, but just to point out, things don't have to decay exponentially. It can decay in other fashion, right? And then half-life is just really the concept that says at a time, when is the time when you have 50% of what you have left? When you understand like that, you can pose the question for anything that decays, right, in any fashion. So yes, I know that people usually use exponential, right, model for that, but there's no absolute connection, right, between that and what you're asking. Yeah. Right, but what are we talking next? Then, so the next thing, right, is this actually has a lot of use. That is, right, it allows you to immediately conclude the integral from 0 to infinity, lambda x eta minus lambda x is equal to 1/λ. So people who knows probability can save their time doing some integration by part by quoting the memory. Again, right, it's legit. Within some circle, within this circle, right, you can do that because this is accepted knowledge. But again, right, I'm saying quoting this is fine. The problem comes when you misquote it, then it's on you, right? So it's up to you to use things correctly. But you can quote it and you just give, it's just like, memorize the formula, right? That's all. Incorrectly, right? So, and then of course the variance can also tells you that the integral from x squared lambda eta minus lambda x is the variance plus the expectation square. So that's that. Right. So that's the advantage of knowing this formula. All right. Now, when it comes to translation and scaling, right, as I talked about before, when you scale an exponential, you still have an exponential, but when you translate an exponential, you do not have an exponential. What's the reason? The reason, right, has to do with the strict definition of the support of the exponential. Right? Actually here, if it's negative as well, because an exponential must have support from 0 to infinity, right? If you translate, then you change the support. If you multiply with a negative number, then you make the support into minus infinity 0. This is C to infinity. Does that make sense? So in either way, right, the shape of the density still look like an exponential, but you have changed the support. So you cannot properly call it a classical exponential. All right. So that's those nuances you have to pay attention to. Right, but let's talk about the memories properly. So here it is, right? And it has to be stated like this, right? That basically conditional on the fact that the event, right, has not happened before time t, right? That's this part. What's the probability that the event will not happen for an additional h unit of time? The answer is, well, it's the same as if at the beginning you wait for the event to happen beyond h unit of time, right? So the memory part, the t that you have waited, does not contribute. All right, so first of all, let's prove this right away, right? It's very quick. Using the definition, right, of conditional probability, the left-hand side is just probably x bigger than t plus h over probably x bigger than t, right? Because I can combine these two together to just t plus h. And then, right, you just kind of integrate t plus h to infinity, lambda e to minus lambda x dx, right? T to infinity, lambda e to minus lambda x dx. And the integral here, right, will become e to minus lambda t plus h, and then e to minus lambda t, right? Of course, canceling the exponential give you e to minus lambda h. All right. Any question about the calculation? Right. So once again, right, let's go back to that question of the uniform, right? Here. Notice it has exactly that form, right? This is t, right? And this is h. This is t plus h, right? And notice the answer is not the same. The answers are not the same. Again, right? I'm not trying to say that this is anything surprising. This is a uniform. But, right, I have had students quoting on me that the uniform is memoryless, which is wrong. Or, right, I guess the other way around, whatever, right? But just to say that, right, these calculations happen for all random variables. For the exponential, right, they're the same. Now, let's talk about the meaning of this, right? What does this mean? The meaning of this is a bit interesting if you think about it. And it's actually not natural. Let's take let's say the standard, right? I'm not sure what you call it standard, but the standard model is the breakdown time, let's say, right? Not standard. But, so what you're saying is that if your instrument has survived, right? This is called survival time, by the way, right? If your instrument has survived 10 years, you know that, right? You use it for 10 years. Then the probability it will survive an extra year, right, is the same as if when you bought new and you ask for the probability you will be able to use it for 1 year, starting from new, right? And that definitely sounds very weird if you look at it from the instrument point of view, right? Because, right, I guess, again, at least for me, a new instrument, right, seems less likely to break down than an old one, whatever. And the problem becomes even funnier if you apply that to human survival, right? And by the way, in the actuarial circle, right, there is a concept called a hazard rate, or, right, they have to look at, human or whatever it is, exploration time, I call it that way, right? So similar concept. So a person having survived, I don't know, 60 years, and probably the person will survive an extra 10 years will be the same as the probability that an infant surviving the next 10 years. Well, doesn't have to say, right? I'm not trying to say which one's high, which one's lower, but that doesn't sound like the same. And so, of course, right, just to point out that if you use the exponential to model, okay, then you're committed to the memoryless property. So if you feel like the phenomenon you're doing doesn't exhibit that, then you might want to step back and look at things, right? But so it's beyond our class as well. But the issue here, the main reason why this fails, or sorry, the memory, well, either works or fail, depends on whether you like the memoryless property or not, right? But the reason why the memoryless property is there is because lambda, right, is a constant. Lambda is a constant, right? And you're like, what? I mean, well, isn't lambda a constant? Lambda is a parameter. Oh, yes, right? But you can move beyond a constant rate here and have, right? This is exactly the actuarial circle where they use the concept of hazard rate. Lambda as a function of x. Then you have to have an integrating constant in front because I don't know what the integrating constant will work with that function. So you would choose a function lambda as the hazard rate. All right. Again, this is beyond our class, but just to let you know, right? So when you let the rate, right, lambda is a rate of breaking down. If you let that move along with the value x, right, then you can make it higher for some range of x and lower for some other range of x. So in that sense, you flexibly, right, tune your hazard rate according to data, right, empirical data, mortality table, whatever you have. All right. But if you use constant lambda, then you commit to memoryless property. Now, what phenomenon, right, exhibits memoryless property, right? Well, your guess is as good as mine, right? But my experience is actually waiting for paperwork to be processed. Sounds like memoryless, right? Because you could have waited for it for 10 years and still not getting your paper processed. Who knows? But things like that, right? But yeah, so right, just pay attention that when you use them, or the exponential classically, right, has memoryless property, right? And it has implications in terms of modeling, right? That you want to at least pay attention to. Okay, any question about this? All right, so let's look at the next problem set. So the exponential is all the way down here. All right, we'll look at that later. Okay, so let's take a look at this. Okay, so lambda, right? So let x be exponential 1/2, right, which is the repair time. So a, right, probably x bigger than or equal to 2 is the integral from 2 to infinity, right? 1/2 e to the minus 1/2 x dx, right, which is 1 minus, right, e to the minus 1/2 times 2, which is 1 minus e to the minus 1. All right. Okay, so far. Oh, sorry. There's no 1 minus, right? All right, any question? So part B, right, what's the probability it will take at least 10 hours given that it exceeds 9 hours? Meaning what? Probability x bigger than or equal to 10 given x bigger than or equal to 9, right? What can we do here?
Use the memory list.
Right. You can calculate straight, right? I'm not saying it's hard, but you can bypass all the writing by using the memory list. You could just say so, right? To say that it's probably x equal to 1. Okay. And using a similar calculation, right? This will be e to the minus 1/2. Any question? Okay. Okay. So I guess that's the only, well, not the only. Now we have this, right? Let's take a look at this. So this is the same question, right? As we just took a look at. That's the one we just took a look at. But this one, right? Of course, the changes, instead of having a uniform, right, from 0 to big A, a finite length road, we have an infinite length road, right, with an exponential lambda distribution. All right. And as I said, this changes everything, right? Because the exponential is a non-symmetric distribution. Now the setup, right, is still the same. In other words, right, we still do minimize, right, over A expectation of x minus A, right? And to calculate expectation of x minus A, look at the integral, but now from 0 to infinity, right? Little x minus A, e to the minus lambda x, lambda dx, right? Which is to A, x minus A, lambda, right? Plus A to infinity. Sorry, right? This is A minus x. Okay, like that. That's a lambda. All right. So the next step will have to be what? The next step will have to be, right, evaluate this, right, as a function of A, and then find f prime of A, right, and set equal to 0. Correct? Now, I'm not trying to say that integrating this is hard or anything like that. But looking at this, right, there's this term right here, which will require me to do integration by parts, right? And it's messy. Hey, messy-ish, it's not terrible. On the other hand though, right, I am differentiating with respect to A, right, little a, of an integral. So let's kind of remind ourselves, at least, is it Calc 1 again, right? Today is a Calc 1 day. Someone tell me what this is. If I differentiate that expression with respect to A, what do I get? Have we forgotten our calculus 1? The answer is A e to minus lambda times A. It's very simple. You just plug A into the integrand, wherever the x is. All right, that's called the fundamental theorem of calculus. Now, what happens if the A is at the lower limits? Can I do that too? The answer is yes. It's just minus. Right, also FTC. Well, does that mean that then I can just apply the fundamental theorem of calculus and differentiate over here with respect to A? And then just basically plug A in. Now notice, right? If I plug A into this expression of X, what do I get? I get 0, right? Because A minus A is 0. If I plug A into here, I get also 0. What's going on here? Does that mean that, remember, right, something has derivative equal to 0 if only it's a constant? Does that mean that this expression is a constant in terms of A? No way, right? So what's wrong? What's wrong is actually the rule here cannot be applied to this yet. It's kind of part of it, but the problem is because A here also appears inside the integrand, right? So what we're looking at is not something like this. It's something like this. So here I'm abstracting right into a integrand that depends on A and X. Okay. So the point here is that A appears on the integrand and also on the limit of integration. What can we do? Well, the idea is, right, just do it like the fundamental theorem of calculus, meaning plug A into the integrand or X is, but also differentiate with respect to the integrand, meaning that you move the integration inside the integrand. Do we understand? So this is called the Newton-Leibniz rule. Which, right, just generalizes the fundamental theorem of calculus. So why bother, you ask? Why bother again, right, is that, yes, you can integrate this out completely and then differentiate, that's fine. It's just, right, sometimes the integration is painful. Like here, right, you have the x e to minus lambda x integration by parts. So remember, right, I'm not trying to say that you do not have to know integration by part for this class. You do, right? That's Calc 2, which is a prerequisite. But if we can use some tools to not do it, why not? So here, right, if I use this rule, the expression will become much simpler, right? If I differentiate with respect to A, so if I plug in A, it becomes 0, right? So it will become the integral. If I differentiate with respect to A, you see, then this part becomes 1. So it's just e to minus lambda x. right? And then if I differentiate it to a here, it becomes -1. So like that. Do you understand? And then we can set that equal to 0. Because that's already the derivative. Well, what is this, you ask? Well, let's calculate out, right? The integral from 0 to a e minus lambda x dx will be, so the lambda doesn't do anything, right? It cancels because you set equal to 0. So that will be 1 minus e to minus lambda a, right? And then minus, this is sorry. You know what? Actually, I need the lambda. Because if I anti-differentiate, I got, right? So I need the lambda there. And then if I integrate here, right, I got e to minus lambda a, right, is equal to 0. Okay? So 2 e to minus lambda a is equal to 1, or a is log 1/2 minus lambda, so log 2 over lambda. Rather a star, right? The optimizer. That's the answer to this question. Any questions so far? All right, so now let's ask, what meaning does this have to the exponential lambda, which is the distribution of x? What role is a star in terms of the exponential lambda? Is it the mean? Is it expectation of x? Clearly not, right? Because expectation of x is 1 over lambda. How do I find the median of the exponential lambda? How do I find the median of the exponential lambda? Well, it's the value, right? That's a half to the left, half to the right. So half to the right means 1/2, right? This is to infinity, correct? But this means e to minus lambda mu hat is 1/2, or mu hat is log 2 over lambda. So that's the median. Any question? All right, so I think it's a good place to stop here, right? And we'll continue on Wednesday. Remember, the midterm 2 is this Friday, right? And the setup will be the same as midterm 1. The materials is up to homework 9, which is the last problem set, right? We covered. This one is on the new problem set, so they won't be on the midterm 2, but will be on the final materials, right? Up to the last one we did, which is the one on your homework 9, right? Okay, so if there's no question, we'll continue on Wednesday.
Professor, so
Yeah.
can I keep on using the bonus points if I didn't didn't need them last time?
Need them? No, the
Like
bonus point. The
the
bonus point
extra
will
4 points. Yeah.
they will be automatically applied to midterm 1. They're already there.
But
So
I got 100, so it doesn't add.
No, it does.
It
Because
does?
the,
Oh.
of course, the assignment for the equipment check has 0 point. Right? So if you have 4 points over 0, the
Ah,
system will, does it make sense?
yep,
So
yep.
so is there, right? It is
Ah.
calculated, but it's just in midterm one as a percentage.
Okay.
So
Okay, it just
you
goes
have,
into overall, pretty much.
you will get 104% for homework 1, whatever that means.
Okay, got it.
Does it make sense? So it's there, it's calculated. Whatever score you get 4 extra points there. I mean, if you have
Oh.
extra points for, right? Because the assignment is worth 0 point. You can check, right?
Yeah.
Does it make
Okay.
sense? That's how it's
Yep.
calculated. All right,
All right. All right. Thank you.
sure.